Okay, before actually going into the experimental part, let me know how many of you have done any kind of experiments at your school level or at your intermediate level. Have done any experiments in your intermediate or 10 plus 2? Yes?
We did titration
Yes, ma'am.
experiments, ma'am.
Okay, you have done titration experiments in chemistry in 10 plus 2 into second year.
Yes, ma'am.
Okay. What titration you have done, ma'am? You remember anything? Acid base titration. It's
Acid
that
base titration, ma'am.
acid base titration. Okay. So strong acid versus strong base. Am I audible?
Yes, ma'am.
Down here, this table column, you can just go through it. Okay. So coming to this part, so these are the important terms: titration, titrant, endpoint, indicator. So all these terms will come across. Okay. While the experiments are being done. So titration means the procedure. The procedure of finding out the endpoint is nothing but the titration. Titrant is the solution what we have taken in the burette. I hope you people remember the burette pipette clinical flask estimation of hardness by ADTA method. Do you remember that?
Yes, ma'am.
Now, titrant is the solution to which the titrant is added. That means the solution what you have taken in the chemical flask will be termed as titrant. And endpoint is whether the reaction is proceeding or progressing or not. Okay, so you can suppose if the reaction is in good progress, then you can locate the endpoint precisely. So that endpoint is nothing. That point is called as the endpoint. And what about the indicator? Indicator is the reagent which is used to identify the endpoint, whether it's reached or not. Next. Primary and secondary standards, this also explained in detail. Okay, so there are some substances you can put them under the primary standard, some of them are called as the secondary standard. Now, what makes a substance to be called as a primary standard substance? Primary substance, the standard substance is something which is pure form, which is stable and crystalline. If all these conditions are satisfied, then that compound is said to be a primary standard substance. For example, if you take oxalic acid, that is crystalline in nature and it is stable and it is readily soluble in water. If these conditions are not satisfied, then the compound could be called as a secondary standard substance. In some cases, like if you are using a KMnO4 solution for this particular titration, KMnO4 crystals are getting oxidized when you just leave it in the end. So that means its concentration keeps on changing. So therefore, you cannot say that that substance is a primary, but rather you can call it as a secondary standard substance. And remember, if I say a primary standard substance, its concentration is known to you. Okay, its concentration is known to you. How? Just by using a formula, molarity equal to weight by molecular weight into 1000 by 100. So you are going to substitute the weight of the compound and its molecular weight into 1000 by how much volume of solution you are using for the dissolution. Like suppose if you are preparing a 100 ml standard solution, then V will be the 100 ml. Okay, so substituting in that equation, you can find out the concentration of the primary standard substance. So therefore, this is said to be a standard solution. So how do you define standard solution? A solution whose concentration is known is said to be a standard solution. And what are the conditions for a substance to be called as the primary standard?
It must be stable and soluble, ma'am.
Yeah, very good. It should be crystalline, stable, and soluble. It should be readily soluble in the water. Okay. So, few examples of primary standard substance would be oxalic acid, then more salt. Okay. So, these are the few examples of a primary standard. Coming to the secondary standard, you have potassium dichromate, KMnO4, then silver nitrate. All these are the examples of the secondary standard. Then there are certain precautions. Please go through the precautions. So this I'll upload in the Teams after the class. Okay, you go through them. So we'll start with the lab experiments. In total, we have 4 experiments. Okay, and first listen to the instructions, girls. So morning by 9 o'clock, you'll be coming to the lab. That means by 9:10 we start our lab session. Am I audible?
Yes, ma'am.
Okay. So by 9:10, everybody will be there in the lab. So from 9:10 to 9:30, we'll just allot your places. Okay, we'll just make you people to stand in your respective places. And two girls will be doing each experiment. Okay, so each experiment will be shared by 2 students from 9:10 to 9:30. Each of the faculty will guide the students like how to use the apparatus and how the experiment has to be performed. Okay, so from 9:30 to 10:30, we will be doing your first experiment. Okay, I repeat, girls, from 9:30 to 10:30, you'll be doing your experiment number 1. Once the experiment number 1 is over, then whatever the readings you have noted down for experiment 1, you are going to substitute in the table column. Okay, in the substitute the table column for the matter what you have already written in the record. So another important point is, before you come to the lab, before you come record work or your record work. So how to write the record? How to write?
Ma'am, your voice is
Yes,
breaking, ma'am.
ma'am.
I'm using the Wi-Fi only, ma. I'm just sitting in front of the
Lot of
desktop.
background noise, ma'am.
Lot of background noise. Like somebody is talking or what from the earphones, or somebody is talking, like what kind of background disturbance you are having.
I think some faculty is speaking in the background.
One second. That you can't help it to.
Yes, ma'am.
One second, one second. Otherwise, I have to raise my volume. I'll just try to increase my volume. Just see here. Okay, just let me know whether my voice is clear or not. Is it clear now?
Yes, ma'am.
Okay. Explain at the end of the experiment. Okay, so first we'll start with the experiment 1. Okay, I'll start with experiment 1. So first experiment is estimation of hardness of water by a complexometric titration using the EDTA. Okay, what is the full form of EDTA? What is the full form of
Ethylene
EDTA?
diamine tetraacetic acid, ma'am.
Very good, excellent, excellent. Okay, you remember the structure? You
Yes,
remember the
ma'am.
structure?
Yes, ma'am.
So you have to be prepared for Viva also, girls, because once you have done with your experiment, so Viva will be taken for all the 4 experiments. So before you come to the lab, you have to complete your record work, you have to prepare for the Viva. So at the end of each experiment, okay, so you have to be thorough with the principal part also. So this is the principal, okay. The theory part is given here in the lab manual, and towards the end of the experiment, you have a list of Viva questions. Along with the questions, solutions are given. Can you see that? Okay, so solutions are also there for that. So we are already providing you people with the ready-made answers. So hope everybody will come prepared for the Viva questions along with the principal part for the exam. Okay. So when you come to the lab on 15th, I hope you have your lab session on 15th, right? When is your lab? 15th, right?
Yes, ma'am.
Yes, when you come to the lab on 15th, you have to be prepared with all these things, because at the end of the day, around 2:30, we'll start your lab internal exam, for which you should be thorough with all 4 experiments. Okay, so from 9:30 we'll start our experiment 1. For every 1 hour, we'll be completing each experiment. Okay, so before your lunch break, we'll be doing 3 experiments. After you come back from lunch, we'll have 1 experiment. and immediately at 2:30 we'll start our lab internal exam. And remember, lab internal exam will be theoretical. Okay, so lab internal exam will not be the way like we won't be giving you any solutions for the titration purpose. So each and every experiment what you're going to perform, that will be monitored very strictly and thoroughly. Okay, so while you people perform your experiment, that itself will be a part of your exam. Okay, so be prepared for the exam. Like, don't think that all these 4 experiments what you're going to do will not fetch for your lab internal exam. Definitely, because we'll keep observing you and we'll note down the way in which you are doing your experiment, and also we keep on asking the viva questions. Okay, so for all that marks will be given, so performance based. And at the end you have your lab internal exam, and that is a theoretical one, purely theoretical one. Okay, so be prepared for each and every experiment. Assume that you are giving your lab internal exam on the day when you are coming to the lab for doing your experiments. Don't think that that is a regular lab, because we are not doing the regular lab sessions. So we are doing all the experiments on a single day. So be prepared for that. Okay, be prepared for that. Am I clear?
Yes, ma'am.
Okay. Now coming to the experiment 1. So here EDTA method is used for finding out the temporary hardness, permanent hardness and total hardness. So you can find out 3 types of hardness. But because of the time constraint, what we are doing is we are just making you people to calculate till total hardness only, because this is only one step we are making you people to do. Okay, so remember, this is actually 4-step procedure. So this is actually 4-step procedure, but you are going to do only one step, because we are providing you with the M2 value. Okay, so here the aim of the experiment will be to find out the total hardness. Total hardness. Now, what is total hardness? Can anybody tell me what is total hardness?
Temporary hardness plus permanent hardness.
Yeah, total hardness will be temporary plus permanent hardness. Okay. So when you have these two together, temporary and permanent hardness, then you can call it as total hardness. Okay. So the procedure is only 1-step procedure. Before actually we go into the procedure, let me make you people about the awareness about the apparatus. So the common apparatus you can remember: a burette, a volumetric flask, a conical flask, a pipette, dropper. So these will be the common apparatus for any kind of your titration. Then coming to the chemicals: magnesium sulfate, EDTA, iriochrome black tea, that is your indicator, then buffer solution and water sample. Okay. Yeah, please mute your mic. Mute your mic. Then next come to the principal part. Okay. So So you will be taking your magnesium sulfate solution in a conical flask. Okay. So I think it's not given here. Okay, I'll directly go to the procedure. Yeah. You will be taking a hard water sample. So what does the hard water sample contain? Hard water means what? What do you understand by hard water?
Does not produce lather, ma'am.
Yeah. Water which does not produce lather with soap. That means what does it contain? Hard water. What exactly is the composition of hard water?
Dissolved salts of calcium and magnesium.
Very good. Excellent. Okay. So hard water contains the salts of calcium and magnesium. Like it can be magnesium carbonates, bicarbonates, sulfates, chlorides. Okay. So magnesium chloride, magnesium sulfate. So all these are your hardness causing salts. Okay. Now, if you take a hard water sample, which actually contains your hardness causing salts, let us imagine magnesium salt. Okay, magnesium salt. Yeah, any problem? I heard somebody talking. Is everything fine?
Yes, ma'am.
Okay. So in the conical flask, when you take your sample hard water, okay. So we, as you know, hard water contains the salts. So this water sample, you are going to add the indicator. What is the indicator here? Iriochrome black tea. Okay. So 2 drops of indicator and 10 drops of buffer solution. Okay, so into the conical flask, first thing is hard water sample, then indicator, then 10 drops of buffer solution. And in the burette you are going to take EDTA solution. In the burette what you are going to take? EDTA solution. Okay, now the moment you add indicated your salt solution, or I can say hard water sample. Okay, so the magnesium ions, the magnesium or calcium, here I can write anything. Okay, this can be calcium even. So magnesium ions or calcium ions present in hard water, it forms a complex with the indicator. What is the indicator here? What is the indicator here?
EBT, ma'am.
EBT. Okay. So you can see there is a complex formation between the metal and the EBT. And what is the color of this? What is the color of this?
Um,
Yeah, here it's written below this. Okay, it's actually a wine red color. So below this you can see it's a wine red color. Now, when you titrate with the EDTA, you can see the magnesium ions which were earlier bound to the indicator, that is the magnesium iridium complex. Okay, so what will happen is slowly the magnesium ion starts forming a complex with the EDTA. Okay, and you know EDTA is actually a 6 donor complex, because here you have 2 nitrogens here, and here you have oxygens, 4 oxygens. Okay, now slowly the magnesium ions will get displaced from this winded complex, and it starts forming a complex with the almost all ions of this winded complex will form a complex with the MgEDTA, and at the end you are left over only with the indicator. Okay, you are left over only with the indicator. Now here you can see there is a complex between metal and EDTA, and this is found to be more stable. As you know, EDTA is a 6 donor atom ligand. Okay, it is a chelating ligand. So this magnesium EDTA complex is highly stable than your magnesium EBT complex. Okay. Now, how do you locate the endpoint? How do you locate the endpoint? So initially you have a violet color solution, and at the end point you have the blue color solution. Now what does this blue color indicate? What is this blue color indicate? Yeah, end point means what? So blue color is because of presence of what? That is because of due to, see here in the equation, it's only just because of the free indicator. Now that you don't have any magnesium ions forming a complex with indicator, slowly all the magnesium ions from this binded complex, they got displaced and they have formed a complex with the EDTA. So this is a Mg-EDTA complex plus EDOT. So that means at the end point, the blue color is because of the presence of the free indicator. You got my point, girls? Have you understood?
yes.
So the blue color at the end point is because of the liberation of the free indicator. So please note down here, if you have any doubts, you can just mention a book for this. So here you can write free indicator. Here also you have a free indicator word. And here you have the free indicator. Okay. So free indicator, liberating the blue colored free indicator. Okay. That's why at the end point you can see the color changes from wine red to blue. Once if you see the blue color, you have to stop the titration. You have to stop the titration and then note down the end point. So note down the end point. So you'll be starting with 0 ml. So initial reading will be 0. So here you can see pipette out 40 ml of sample hard water into clean conical flask. So pipetting out the 40 ml, it's a time taking process. What you can do is you will be given a measuring jar. So directly you can measure 40 ml from the tap. Okay, from the tap you can directly measure 40 ml into a measuring jar and put it to a keep it and transfer this water into a conical flask. Okay, now. Add 2 ml of buffer solution. 2 ml means that roughly comes around 10 drops of buffer solution and then 3 to 4 drops of ethiopia plastic. Now titrate the solution with the standard ADTA solution and the color changes to blue color at the end point. Now each one of you, like in total only 2 titrations you are doing. Okay, this already I told you. In total, you are going to do only 2 titrations. So since anyhow in a batch 2 girls are there, so each one of you have to do this titration, girls. Okay, because this will be a practice for you, and this will not be a burden for one girl. So both of you have to do the experiment. We'll just keep watching you whether you are doing or not. Okay, so 2 titrations, each of you doing 1 titration, and here you can substitute. Okay, so this is the serial number. So remember, so these tabular columns should be written on the left hand side. So you have to draw these tabular columns on the left hand side in your record book, and this will be written, the theory part will be written on the right hand side. And here, yeah, once the blue color is obtained, you can stop titrating and then turn off the knob of your burette and substitute the values here. So here serial number 1, volume of hard water, how much you have taken? 40 ml. Okay. And what is VI? VI is nothing but the initial reading, initial burette reading. Okay. So always you start with 0 ml. So you can just take substitute here 0. And VF. VF stands for V final. So V final is like where you 25 or 27 or 30 or 40, like each one of you will be getting a different reading. So please don't compare with the others reading and then substitute. Okay, so don't copy from them or don't compare your readings. Okay, each of you will be getting different reading because you have lots of experimental errors are there. So unless we rectify all these things, values will not be same. Okay. So just follow the instructions, do the experiment, substitute the initial value, and final will be like suppose at 25 ml. At 25 ml you have observed the blue color. Okay, then you have to turn off your knob of your burette and then shake your solution thoroughly and see whether it has a persistent blue or not. And another important point is whenever we give any endpoint, after noting down the color change, what you have to do is shake the solution thoroughly. Okay, shake the contents thoroughly so that whatever the expected color is there, that will be retained. If it is not retained, then what you are going to do? Like for suppose, actually the expected endpoint is blue. Okay, when I have shake the solution, the blue color got disappeared and it's still existing as wine red. What I need to do at this point of time? What I should do?
Again, we need to titrate.
Yeah, very good. So again, we have to add EDTA from the burette. So just now what we have thought, once the blue color is reached, we just have to close the burette. Okay. So when you shake and see, if the solution color persists, whatever the expected color is there, if it persists, then no need of adding extra amount of the EDTA. But otherwise, we just have to add few more drops of EDTA from the burette. Few more drops of EDTA from the burette, and make sure that you have the blue color, persistent blue color for your solution. Okay. So then you can note down the end point here, V final. Now V2 will be what? V2 will be the difference of V final and V initial. So that value you are going to note down here. So likewise, similarly, copy the second titration, the titer value also. So do the titration first, then substitute in the given tablet column. Okay. Now coming to the calculation part. Here you have the hard water sample versus EDTA. So for hard water, we have the things as 3, M3, V3 and M3. And for EDTA, we have to consider this as M2, V2 prime and N2. Now, what is the step 2 value? Step 2 value will be actually given to you. I'll just let you know how much is the step 2 value. Now, what is V2 prime?
Burette reading.
Yeah, burette reading. How much is here? Like suppose the initial value is 0 and final value is 25. So what is the burette reading then?
25.
25, very good. So that value you are going to substitute here. And what is that you are going to calculate now? M2 is given to you already. I have written here. Okay, from the step 2 values. M2 is 0.01. V2 prime, already you know this is 25. Okay, in this case, just we were actually talking about one example. So don't substitute 25 here. This you have to substitute only after doing the titration in the lab. So when you come to the lab, you will be doing your experiment and noting down your own reading. Don't copy 25 there because 25 is not a common number. Have you understood what I am trying to tell you?
Yes, ma'am.
Okay. Now M3 equal to M2 V2. So you have a formula M3 V3 by N3 equal to M2 V2 by N2. So substitute in that equation and get the M3 value. Once M3 value is known, this M3 value you multiply with 10 power 5, then you get the amount of total hardness in ppm. Understood? So how many steps you are doing finally in the lab? Yes, how many steps you are doing in the lab? Titrations, how many steps you are doing in the laboratory? 3 steps, sir. Did I explain 3 steps? This is actually step 3, but there are no 3 steps. This is step 3. Okay, so here you are going to do only one step, that is the estimation of hardness, total hardness of water, because we are directly providing you the M2 value. Actually, in the step 1, you are going to prepare a primary standard solution, and in step 2, you are going to standardize that, get the step 2 value, substitute here, and substituting all these things, you can find out the N3 value. Okay, fine. Are you following, girls?
Yes, ma'am.
Now we'll again come back to the principal part. Okay. Here, hardness of water is because of the presence of dissolved salts. We have already discussed about this. So indicator EDTA structure. Now, what is the pH used here? The EDTA titration is sensitive to pH. A buffer solution, this is very important Viva question. A buffer solution combination is weak base strong acid or strong acid weak base combination, and it starts with the this is your salt, NH4Cl is a salt. So this is your weak base and it starts with the strong acid. So NH4Cl plus NH4OH. This is the buffer used for EDTA titration. Now why do we add a buffer? We add a buffer in order to maintain a pH 10. Okay, in order to maintain a pH 10. Now at pH 10, we have a stable either magnesium EDTA or calcium EDTA complex. Okay, so for which we require buffer. I already told you are going to add 10 drops of buffer. So what is the role of buffer here? What is the role of buffer?
To maintain pH.
To maintain
Yeah,
pH
yeah,
distribution.
to maintain pH 10. Okay, but not only that, even the metal EDTA complex is more stable at this particular pH. At this particular pH. Now, if you see the order of stability, calcium EDTA is more stable than magnesium EDTA, which in turn more stable than Mg-EDOT, and then finally the least stable one is calcium EDOT complex. Yeah, any doubts? Yeah, any doubts in the experiment one? Okay. 2 minutes. I want everybody to go through the Viva questions. Okay. If you have any doubts, we'll discuss. Just 2 minutes. I'll just come back in a minute. Go through the Viva questions, girls. Is it okay?
Yes, ma'am.
Yeah, go through the Viva questions. I think all of them you can answer them very well. Have you read these questions, girls?
Yes,
Okay.
ma'am.
Shall I scroll down? 3 more questions are there. Shall I ask you a question? What is the role of a buffer? What is the role of a buffer?
To
Maintain
maintain
pH.
To maintain a pH 10. What is the, which buffer is used here?
NH4Cl plus
NH4
NH4OH.
Very good. How to convert the molarity into ppm?
multiply with 10 power 5.
Very good. How many steps you are doing? How many
One.
steps you are doing in the lab?
One. One.
Only one step. Only one step. Which type of
One.
salts causes permanent hardness?
Chlorides and sulfates of magnesium and calcium. Chlorides and
Yeah,
sulfates of
very
calcium
good.
and magnesium.
Very good. Very good. How many donor atoms are there in EDTA? How many donor atoms are there in the EDTA?
6.
So therefore, this ligand is called as. Therefore, this ligand is called as. 6 donor atoms containing ligand will be called as what?
Polydentate ligand.
6 means you remember monodentate, bidentate. So therefore, it is
Hexadentate.
hexadentate ligand. What is the color of magnesium EDTA complex? What is the color of magnesium EDTA complex? Yeah, yeah. There everybody will commit a mistake. Magnesium
No color.
EDTA complex. Yes?
No color.
Yeah, very good. So magnesium EDTA is colorless. Please make a note of this point. Magnesium indicator is wine red. And why do you get a blue color at the end point? Why do you get a blue color at the end point?
Free indicator.
Because
Because of the presence of free indicator. Because when you titrate with the EDTA, what will happen to all the magnesium ions which were earlier bound to this complex, EBT complex, all these ions will slowly get displaced and ultimately it forms a Mg EDTA complex, leaving behind the free indicator in the solution. So that's how you can see the blue color for your solution at the end point. Am I clear?
yes.
Okay. How do you convert ppm into degree Clark? How do you convert ppm into degree Clark?
0.07 degree. 1 ppm.
Yeah, 1 ppm equal to 0.07 degree Clark. Likewise, degree French, 10 mg per liter. So while I'm doing your experiment in the lab, then you'll get some doubts. Shall we go on to the experiment number 2?
Yes, ma'am.
Okay. So experiment number 2 is estimation of ferrous by permanganometry. So here you will be given ferrous salt. So in that given amount of the ferrous salt, how much amount of ferrous is there? That is what you are going to find out by using a KMNO4 solution. So permanganometry titrations means what? Why the titrations are called as permanganometry? Why the titrations are called permanganometry titrations? Because here you are using the KMNO4 solution for the titration purpose. So in the burette, what you are going to take here? In the burette? No, burette. In the burette, what you will fill the burette with? So anything you are estimating, like suppose if a given solution is there, a particular unknown solution is there, you have to find out some iron or something else present in that solution. So that solution has to be taken in the conical flask, and in the burette you are going to take the KMNO4 solution. Am I clear? So estimate the amount of ferrous ion in the given solution by preparing standard oxalic acid solution and using the link KMNO4 solution. So you will be given the data of M2, that is the concentration of KMNO4. So therefore directly you have to calculate the concentration. First you have to calculate the concentration and finally amount of the ferrous in the given solution. Okay. So burette has to be filled with what?
KMNO solution.
Very good. Burette is filled with the KMNO4 solution. And what is that you are going to take in the conical flask?
Ferrous solution.
Yeah, the solution, or I can simply say unknown solution. A solution whose concentration you are going to find out, you are going to just take in a conical flask. So conical flask is used for the titration purpose. Remember that conical flask is used for the titration purpose. Now coming to the apparatus, already I told you, you can find the common apparatus, burette, conical flask, pipette, standard flask and funnel. And what are the chemicals you require for this? Can somebody read out?
Ferrous ammonium sulfate, dilute sulfuric acid, potassium permanganate solution, oxalic acid.
Okay, good. Now, these permanganometric titrations, these are a special class of titrations where you can call them as the redox titrations. Okay, so these are called as the redox titrations. Now, why they are called as redox titrations? Any idea? Why do you call the titration as a redox titration?
Reduction takes place. No.
What takes place? Reduction.
Undergo self-reduction.
Sorry, can you repeat it? What you said? Yes. Only reduction is taking place.
Oxidation also.
Yeah. Redox titration means both oxidation and reduction are occurring. Okay. So KMnO4 is a powerful oxidizing agent and therefore it oxidizes. Okay, it oxidizes. So any oxidizing agent means what kind of reaction does it undergo? KMnO4 is a very good oxidizing agent. So that means will it undergo oxidation process or reduction process?
Reduction.
Very good. So anything which is an oxidizing agent will oxidize the other substance in the solution and that itself getting reduced. Okay. So if you go through this reaction where you have a reaction between the KMnO4 and oxalic acid. H2C2O4 stands for oxalic acid. So how do you know whether any substance is getting oxidized or reduced? How can we say, suppose if I say KMnO4 is a oxidizing agent or that means it is a undergoing reduction. How can I say that? This is the required reaction or the equation, chemical equation. Yes? No idea? Calculate the oxidation state of manganese in KMnO4 and again get the oxidation state of manganese in MnSO4. Then oxidized. Yeah, calculate the oxidation state of manganese in KMnO4. So how to calculate the oxidation state of manganese here? You know how to calculate? I think this is a very simple question what I have asked you. Can anybody calculate and tell me how much is the oxidation state of manganese in KMnO4? No one knows how to calculate the oxidation state. Come on quickly girls, don't waste my time.
+7.
Yeah, very good. +7. How did you calculate +7? How you are getting +7 value here?
Ma'am, oxidation state of K is 1 and O
Oxidation.
is 2, ma'am.
Okay, so K is +1, manganese X and oxygen is -2. So +1 plus X minus 8 equal to 0. The total will be equating to 0. So then X minus 7 equal to 0, X equal to +7. So +7 is oxidation state of manganese and KMnO4. And how about MnSO4? How about MnSO4? Yes, girls?
+6, ma'am.
How ma? +6?
Oxidation
Sulfate
state of
as
sulfur is +6.
sulfate. Mhm. Sulfate as a whole you have to calculate. Okay, sulfate is -2. So X minus 2 equal to 0. So X equal to +2. So from +7 it is changing to +2. Is there increase in the oxidation number or decrease in the oxidation number?
Decrease.
Decrease in oxidation
Decrease.
number. Okay. So if there is any decrease in oxidation number, then we can say that that substance is getting reduced or it is acting as an oxidizing agent. Okay. Now, the same thing here also you can see. So in this process of reduction, okay, KMnO4 is oxidizing ferrous to ferric. Okay, ferrous to ferric. So this first equation, whatever you see, that is the reaction between KMnO4 and oxalic acid. This is what we are talking about in the step 1. Okay, and then next step 2. In the step 2, what is done is you are taking ferrous salt solution in the conical flask and you are making the KMnO4 to react with the ferrous. So since KMnO4 is a very good oxidizing agent, so this is oxidizing ferrous Fe+2 ions to Fe3+. So in this process, KMnO4 is getting reduced from +7 to +2 and ferrous is getting oxidized from +2 to +3. So from iron +2 to iron +3, do you see there is increase in the oxidation number or decrease in the oxidation number?
Increasing.
Increase in the oxidation number. So you might have learned that with increase in the oxidation state of any species, that indicates that it is getting oxidized. Earlier in KMnO4, did you find change in oxidation number, right? From +7 to +2. Is that increase or decrease? From +7 to +2, it was actually decrease in oxidation state. That means it is getting reduced. And here you can see there is increase in oxidation number from +2 to +3. So therefore, this is getting oxidized. So these equations you are supposed to write. In coming to the principal part in any type of titration, so this entire thing thoroughly has to be mentioned in the exam. Okay, so this you have to read it thoroughly. So this is about the principal part of the experiment. Now the next coming to the chemicals required. So what are the chemicals required? Ferrous ammonium sulfate, then dilute sulfuric acid, potassium permanganate solution and oxalic acid. So for the step 3, so for the single step titration what you are doing, so into the conical flask, into a clean conical flask, you will be taking the unknown solution. Now what does this unknown solution contain? We are calling this as unknown solution. Now which is that unknown solution? KMnO4 is oxidizing what?
Iron.
Iron. Okay, so finally, what is the title of the experiment? Estimation of ferrous by permanganometry. So you are going to estimate how much of the ferrous is present in the given solution. So in the for the titration purpose, you will be provided with the unknown solution. So what is that unknown solution? That unknown solution is nothing but ferrous solution. So here we are going to find out or estimate how much amount of ferrous ion is present in the given solution. So for this, the procedure is like this. Into a clean conical flask, take the unknown solution. So unknown solution refers to what? Unknown solution refers to the ferrous solution, ferrous ion solution, and you don't know the concentration. So by using this titration, you can do the calculation and get the concentration of the ferrous. Okay. So into the clean conical flask, you will be taking a known quantity of unknown solution of iron. Okay, and then add 1 test tube full of dilute sulfuric acid. Okay, so what is that you are adding? You are adding 1 test tube full of dilute sulfuric acid and then titrate with the KMnO4. Titrate with the KMnO4. But we have not added indicator here. We have not used indicator here. Then how can we locate the endpoint then? How to get the endpoint? Because here we are not at all we get the endpoint. How is it possible?
Change in color.
A change in color. How is that possible? Because we are not using any indicator, no? Because in the estimation of hardness, I told EBT is used as indicator, but we didn't mention anything about the indicator in this experiment. What is the reason for that? Because KMnO itself acts as a self-indicator. That's why you don't require any external indicator here. Have you understood what I'm trying to tell you?
Yes, ma'am.
So, into the conical flask, sulfuric acid. Now titrate with the KMnO4. So KMnO4 solution must be taken in what? Which apparatus?
Burette. Burette. No.
Burette. Very good. In the burette, you are going to take KMnO4 and then titrate with the unknown solution. What you have taken the clean conical flask. Okay. So while you are titrating, so the end point would be the faint pink or pink color, just pink color. It should not be too dark. Okay. So in the process of oxidation, because KMnO4 is a very good oxidizing agent, so therefore this oxidizes ferrous to ferric. This oxidizes ferrous to ferric. So as the ferrous is getting oxidized to ferric, so once all the ferrous ions are completely oxidized, please follow this point carefully. So when all the ferrous ions are completely oxidized by KMnO4, okay, then the next drop of KMnO4 what you are adding, that will actually give you the pale pink at the end point, because once if KMnO4 is getting converted to Mn2 plus, there won't be any change in the color at the end point because Mn2 plus is colorless. Only the KMnO4 is a colored species. Okay, KMnO4 is a colored species, whereas Mn plus 2 is colorless. So therefore, how you are going to get the end point? So when all the ferrous ions are completely oxidized to ferric, the next drop of KMnO4 what you are adding, that will impart a pink color to your solution, and that's how you get the end point and you can note down the burette reading. So here you have started with the 20 ml, you will be taking 20 ml of unknown FAS. Initial reading will be 0, final reading will be like depending upon the color change, you are going to note down the final reading. It may be a 20 or 22 or 23. So each one of you will be getting a different reading. Okay, so here final value you are going to substitute, and difference of these two will be the amount or the volume of KMnO4 run down from the burette, that you are going to substitute here. Here also only two titrations. Each girl will be doing one titration. Okay, so note down both the titer values in the tabular column. And then how to calculate the M3. So M3, how to calculate M3? So you have a formula M3 B3 by N3 equal to M2 B2 by N2. Okay, using that formula, substitute all these things and get the M3 value. So again here you have step 2 value. So step 2, how much that we are going to provide you. KMNO4 is 0.02. So this value you can directly write in your records, girls. So this value you can write down in your record. Step 2 value 0.02 because this is already provided to you. And here you can note down the number of moles from the balanced chemical equation. Here you have the number of moles 5. So here you can write 5 moles of FAS and 1 mole of KMNO4. And V3, how much unknown solution you have to take is 20 ml. And V2 prime is burette trading. So which burette trading I am talking about? Which burette trading am I talking about? So this one, the initial value and final value. Am I audible? Am I audible?
Yes.
Okay. So you understood what is burette trading, no? So initially you have started with suppose 0 ml. Okay, final value is 25 or 26. That value. So different trading will be your burette trading. Understood my point? Okay. Now, once the M3 value is known, multiply that with 56 to get the amount of ferrous ion. Amount of ferrous in 100 ml will be equal to M3 into 56 by 10 will be equal to amount per 100 ml. So follow this calculation. Now coming to the Viva questions. Any doubts in this principal part and the procedure? Yeah, any doubts in the experiment with regard to the permanganometry? Say yes or no. Whether you have followed or not.
Yes, ma'am.
Okay. So coming to the Viva questions, what is redox titration? This already we have learned what exactly is redox titration. Those reactions wherein you have both oxidation and reduction taking place simultaneously. What is permanganometry? Just go through this. Just go through this. If you have any doubts, I'll explain you. Any doubts? Any doubts? Can you? Can you hear me, girls?
Yes, ma'am.
Okay. Yeah, any doubts with regard to the Viva questions? Otherwise, I'll ask you a question, girls. Why are we adding dilute sulfuric acid, but why not dilute HCl or HNO3 here?
Dilute sulfuric acid is more strong, ma'am, compared to HCl and H.
The HNO3 is not added because it is a stronger oxidizing agent than even the KMNO4. Okay, so this is not used, and even HCl is not used. Why HCl is not used? Why HCl is not used? Because this will liberate chlorine gas. So chlorine gas is liberated. So therefore we are not preferring either HCl or HNO3. So we have to use only dilute sulfuric acid. But what is the role of this dilute sulfuric acid? What's the role of dilute sulfuric acid? What is the need? What is the necessity of adding dilute sulfuric acid to the reaction mixture? Because to prevent hydrolysis of ferrous salts. To prevent hydrolysis. Suppose if you don't add, what will happen? To prevent the hydrolysis of FAS, that is the ferrous ammonium sulfate, to prevent hydrolysis of FAS. Otherwise, what will happen? FAS, that is ferrous ammonium salt, gets converted to FeOH twice. FAS will get converted to FeOH twice. So to avoid this, so this is the hydrolysis reaction. So to avoid the hydrolysis of ferrous salt, we are adding dilute H2SO4. Why do you get a pale pink color at the end point? Why do we get a pale pink color at the end point? Girls? Why do we get a pale pink color at the end point? Quickly, girls.
Because of KMN.
Because of KMNO4. Because initially when you keep on adding KMNO4, it is used up for the oxidation of ferrous to ferric. Once all the ferrous is converted to ferric, the next drop of addition of KMNO4 will impart the pale pink color to the solution. Because otherwise what will happen if you are not if you are just thinking about the color of Mn plus 2, because KMNO4 is getting reduced Mn plus 2, Mn plus 2 is colorless, whereas Mn plus 7 is colored. Any doubts with regard to the experiment 2? I'm just yeah. From the beginning, I'll just scroll down, just see and let me know if you have any doubts. So everybody has to be thorough with the principal part. So this entire thing you are going to write in your lab internal exam. So if you miss these things, so you'll be losing the marks, girls. Aim which kind of experiment and principal part, and then procedure in brief. 2 lines procedure you will be writing, that's it, because you have everything only for a single step, so not much procedure is required. And then draw this tabular column and show the calculations and finally the result. Yeah. Sorry, your voice is breaking, ma. Let me please repeat it.
Ma'am, can you explain again the use of dilute H2SO4, ma'am?
Dilute H2SO4, that is to prevent the hydrolysis of ferrous ammonium sulfate. So this is the more salt what I am talking about. Okay, so this is your more salt. What is the formula of more salt? FeSO4, NH4 taken twice, SO4, 6H2O. Okay, so that is your more salt. So this is actually giving the ferrous ions into the solution. So if you don't add H2SO4, this Fe plus 2 ions, Fe plus 2 ions gets hydrolyzed like this. You have a reaction between the water molecules and the Fe plus 2 and forms ferrous hydroxide plus 2H. So we don't want this reaction to happen. So for this purpose you are adding H2SO4. We want ferrous in FeSO4 state but not in FeOH twice. Understood? Any more doubts in experiment 2, because I'll be starting with experiment 3 now. If no doubts, we'll proceed to the experiment 3.
Yes, ma'am.
Okay. So third experiment is again estimation of ferrous only by using a different kind of an oxidizing agent. So what was the earlier oxidizing agent used in experiment 2 for the estimation of ferrous?
Permanganate solution.
Permanganometry. Okay, but the same estimation you can do it even by using dichrometry. We'll see how this procedure is different or what is the principle behind the dichrometry, how it changes with the permanganometry. Okay, so the aim remains same, to estimate the amount of ferrous in the given ferrous ammonium sulfate salt solution by using the dichrometry method. And chemicals keeps changing phase you have. So then you have K2Cr2O7, this is the titrant, and then you have the sulfuric acid, phosphoric acid, and an indicator. Diphenylamine is an indicator here. This is your indicator. Please underline them because you will be asked what is indicator for your Viva questions. The next apparatus, common ones. The formula of more salt, FeSO4, NH4 twice SO4, 6H2O. That is the formula of more salt. Underline that. This is your more salt. So here also you are going to see the oxidation of ferrous to ferric. Okay, the oxidation of ferrous to ferric. Here you can see ferrous ions present in the solution. They get oxidized in the presence of dichromate. Okay. Now who will calculate the oxidation state of chromium here in Cr2O7 2- and Cr3+? Quickly girls, calculate and let me know. Oxidation state of chromium. Yes? How much? Anybody is doing it or not? This is 2 chromium markers, so therefore 2x plus how many oxygens are there? 7 oxygens. Each oxygen carrying -2. This entire thing equal to -2 because the oxidation number of this entire thing is -2. So 2x minus 14 equal to -2. 2x equal to -2 plus 14 will become 2. So therefore x equal to 6. So oxidation state of chromium here is +6. From +6 it is getting converted to +3. So is there increase in the oxidation number or decrease in oxidation number? Is this +6 to +3? Decrease. So therefore it is getting oxidized or reduced. Decrease in the oxidation number means decrease in oxidation number. Just now we have discussed why very poor response. Decrease in oxidation number means what? Is it reduction in oxidation?
Reduction, ma'am.
Reduction. So chromium is getting reduced and which is getting oxidized? Which is getting oxidized? Ferrous. Fe plus 3 to this is Fe plus 2. This is getting oxidized to Fe plus 3. Fine. This is plus 2 to this is plus 3. So increase in oxidation number here. Here we can write here this is increase in oxidation. Termed as oxidation process. Can I call this as a redox titration? Can I call this as redox titration? Yes, because both oxidation and reduction are happening. The next one. Reaction. Now, when you titrate with the dichromate, like you will be taking the unknown solution in the conical flask and titrate with the dichromate, okay, you can see a green color, okay, you can see green color initially, okay. Now, why is that green color? The green color is because of the presence of chromium. So, during the process of the reaction between ferrous with the dichromate, what is happening? Iron is getting oxidized to Fe3+. And these are colorless, so therefore you don't have any problem with them. But dichromate is getting converted to chromium 3+. And you know the color of chromium 3+? Chromium 3+ is green in color. Chromium 3+ is what? It is green in color. Okay. So as the dichromate is getting converted to Cr3+, as it is getting reduced, you can see the green color, and this green color will remain as it is even after the end point. So even after the end point, the color of the solution will not change. So how will you identify the end point then? Chromium, it is getting reduced to chromium 3+ in the process of oxidizing Fe+2 to Fe+3. So this green color will remain as green only even at the end point. So can you locate the end point if the green color solution still remains as it is? Yes? Am I audible, girls? Am I audible?
Yes, ma'am.
Yes.
You understood my question? Have you understood my question?
Can you repeat again?
See, dichromate is getting reduced to chromium 3+. Okay, and iron is getting oxidized to Fe3+. So during this reaction, you see a green color. The green color is because of the formation of chromium 3+. So this color keeps on like this color keeps on imparting from the beginning of the reaction itself, because here it is getting reduced and this is getting oxidized. So here you cannot locate the end point because the green color is being imparted by the dichromate from the beginning and during the reaction. So for that reason we have to add an indicator which is called as a diphenylamine. Have you understood now why the indicator is used?
Yes, ma'am.
Earlier, if you compare the KMnO4 reaction, did we use any indicator there?
No, ma'am.
No. Why? Because there KMnO4 during the reduction it is getting converted to Mn2 plus, and Mn2 plus is colorless. Mn2 plus is colorless, so therefore there was no problem with the identification of the color change at the end point, because at the end point the KMnO4 which is added an extra amount that will actually impart the pink color. But here, as the reaction is proceeding, the green color remains as green only. There won't be any change in the color. Okay, so you cannot identify the endpoint, for which you are going to add 3 to 5 drops of the diphenylamine. Okay, understood now why the indicators are used in the dichromatic titrations but not in KMnO4. This is the reason. Okay. Now, another important point is, why are we adding the mixture of H2SO4 and H3PO4? Okay. So here H2SO4 is added to prevent the hydrolysis of ferrous sulfate. Okay, to prevent the hydrolysis of ferrous sulfate salt. This point already we have discussed in KMnO4. The same reason here also applicable. And what is the reason for adding H3PO4? H3PO4. Okay. If you see here, what is the reduction potential of diphenylamine? How much is given here? What is the reduction potential of diphenylamine?
0.76.
Yeah, this is 0.76 volts. Okay, and the reduction potential of ion couple is 0.77 volts. 0.77 volts. The reduction potential of ion couple is 0.77 volts. Whose value is high among these two? Diphenylamine is having 0.76 and iron is having 0.77. Whose reduction potential value is high?
Diphenylamine.
Iron couple is 0.77. Iron couple is 0.77 volts and DPA reduction potential is 0.76 volts. Whose value is high?
Iron, ma'am.
Iron. Okay, so this value is high. Now whenever any species whose reduction potential value is high, okay, this gets oxidized. Okay, so this gets oxidized first. This gets oxidized first. Now, if iron is getting oxidized first in preference to DPA. I repeat, girls, if iron is getting oxidized in preference to DPA, can you identify the color change? That means the iron couple is getting oxidized first and DPA is remaining in its original state only. It is not getting oxidized. But we want the color change at the end point only when the oxidation of DPA is occurring. Only when DPA is getting oxidized, you can see a blue color at the end point. But here, because of the variation in the potential values of iron and DPA, okay, as you are observing, there is a higher value of reduction potential value for iron. So therefore, this preferentially gets oxidized, okay, oxidized than DPA, and therefore you cannot identify the endpoint. So for that reason, you are adding phosphoric acid. What is the role of phosphoric acid? Phosphoric acid, when added to the solution, this will form a complex with iron and try to reduce this 0.77 volts. Okay, this will be reduced to 0.44 volts. Now what will happen? Which one will get oxidized first?
DPA, ma'am.
Yeah, DPA. When DPA gets oxidized, you can get the end point, because DPA in its oxidized form only it is showing the color change at the end point. Is this point clear? What is the role of phosphoric acid? What is the role of phosphoric acid? Phosphoric acid when added will form a complex with iron and reduces its reduction potential from 0.77 volts to 0.44 volts. So therefore the DPA now will be having, whose potential will be high now?
DPA.
DPA. Now which one will get oxidized first?
DPA.
Is the DPA getting oxidized first or iron getting oxidized first? Here you can see, in order to prevent the oxidation of DPA before the oxidation of iron. So we want the oxidation of iron first and then DPA. Since its potential is reduced, so first iron gets oxidized, okay, then the DPA will get oxidized, indicating the end point, that is the color change at the end point. Am I clear now?
Yes, ma'am.
Yes, ma'am.
Now, coming to the procedure, so you will be taking 20 ml of the, you will be provided with the 20 ml of unknown solution in a conical flask, and to this you are going to add a test tube full of acid mixture, okay, that is H2SO4, H3PO4, and then dilute to about 75 ml of, like you can add 75 ml of distilled water to this, and then add 4 to 5 drops of the diphenylamine indicator. Now titrate the solution against the potassium dichromate. So potassium dichromate must be taken in the burette. Okay, potassium dichromate must be taken in the burette. And while you are titrating the unknown solution with dichromate, remember first which color do you observe? First, which color do you observe when you are titrating with potassium dichromate?
Green.
Green color, very good, excellent. But don't think that the end point has attained, because the dichromate during its reduction process it gets converted to chromium and imparts green color. That is not the end point. So you have to titrate your solution. You can continue the titration until you observe a violet color at that point. So you have to see the color change from colorless solution to the violet color at the end point. So please do remember this point and do the titration 2 times and note down the value and use this equation M2 V2 by N2 equal to M3 V3 by N3, and step 2 value for K2CR2O7 is 0. Here I'll just type this value. 0.0175. Zero point 0.0175. Okay. Now burette reading is, you just have note down from the burette, okay, and substitute in this equation. And number of moles, how do you get? So from the balanced chemical equation. Here you have 6 moles and chromium is only 1 mole. So substitute in this equation, get the M3 value. Once M3 is known, multiply with 56 by 10, because we are finding out how much amount of solution 100 ml. So therefore divide by 10 to get the amount of ferrous in grams. Very simple. So 2 titrations each batch. Any doubts here? Any doubts here?
No, ma'am.
Meanwhile, go through the Viva questions. If you have any doubts, you can ask me. Go through the Viva questions, girls. Am I audible? Am I audible?
Yes, ma'am.
What is the color of diphenylamine? What is the color of diphenylamine? What is the color of diphenylamine?
No, ma'am.
Yes, diphenylamine is colorless. Diphenylbenzidine is blue. That's what such questions will be asked in the Viva. Diphenylamine in its reduced form it is colorless, whereas in its oxidized form diphenylbenzidine is blue color. That's why diphenylamine is not imparting any color the moment you add, but during the reaction when it gets oxidized, okay, that gives diphenylbenzidine. What is the role of phosphoric acid? What is the role of phosphoric acid?
To reduce the reduction potential of ferrous.
To reduce the reduction potential of iron. So remember this point. Whichever species has lower reduction potential, will get oxidized first. Lower reduction potential. The one which has lower reduction potential will get oxidized first. Now which one will get oxidized first? Is it the diphenylamine or iron?
Iron, ma'am.
Iron. Okay. So once all the ferrous ions are completely oxidized to ferric, then the DPA gets oxidized. This is what we want. Then DPA gets oxidized. At this point you have to remember. So the one which is having lower reduction potential, that is 0.44, okay, will first get oxidized. So this indicates the completion of the reaction, right? We want all the ferrous ions to get oxidized. So how is it indicated? Only by the color change by the DPA. And when does that will happen? That will get oxidized only after all the ferrous gets oxidized. We want DPA to get oxidized after the oxidation of the ferrous. So that's why we are adding H3PO4, which actually reduces the potential from 0.77 to 0.44. Yeah, any doubts still here? Otherwise, I'll just conclude with the last experiment. Just go through them. We'll start with experiment 4.
Yes, ma'am.
So, coming to the last and fourth experiment. So, here you are going to estimate the chloride ions by argentometry. Now, what is the necessity for the estimation of chloride ions? So if you see in water, usually the chloride ions are present as sodium chloride, magnesium chloride and calcium chloride. Even though the presence of chloride ions, it does not cause much harm, but if its concentration is too high, if it is more than 250 ppm in the water, this actually causes a peculiar taste and smell, odor, okay, we just don't feel like drinking that water sample. So that is mostly unacceptable for drinking purpose. So that's why we want to estimate the amount of chloride ions. If it is really high, then we can say that that particular water sample or it's a highly polluted because the pollution can be either from domestic sewage or from industrial wastewaters. So identification of chloride ions will help us to check whether that water is feasible for drinking or not. Okay, so and not only that, if you remember the presence of chlorides in the form of magnesium chloride in the boilers under high temperatures and pressures, the magnesium chloride gets hydrolyzed and gives HCl, and this HCl produced will actually causes the corrosion of the boiler parts. So therefore, these are the important applications, like where, in what way, if you estimate the amount of chloride ions in the water sample, in what way that is helpful. Okay, so then coming to the experimental part. So here we are going to estimate the chloride ions by using the standard silver nitrate solution, and the indicator used is potassium chromate. Potassium chromate is the indicator, and the solution is AgNO3. So AgNO3 solution must be taken in the burette, and in the conical flask you will be taking the sample, unknown sample containing chloride ions. Okay, as you are titrating, what will happen is the chloride ions present in the sample will react with the silver ions. Okay, so here I'll just draw this. So this is what is this called as? What is this? What is this?
Burette and conical flask.
Very good. This is burette. Burette contains silver nitrate, and conical flask contains the sample. That is unknown chloride ions, unknown concentration of chloride ions. Okay. Now to this you are going to add indicator. What is the indicator? Potassium chromate. Potassium chromate is the indicator. So initially when you start titrating here, so when you start titrating here the solution, okay, the chloride ions of this sample will react with the Ag plus from the burette. These ions are added, and here the chloride ions in the sample or in the conical flask will react and forms silver chloride precipitate. And silver chloride is a insoluble white precipitate. Once all the chloride ions of this sample have reacted with the Ag, so that means now all the chloride ions of your sample are converted to AgCl. Okay. Now the next drop of AgNO3 what you are adding from the burette, that will react with the potassium chromate. So when does the reaction happens between the silver nitrate and potassium chromate? Only when all the chloride ions of your sample are precipitated in the form of AgCl. So the next drop of addition of AgNO3 now will react with the indicator, and that actually gives a red color solution, reddish brown color solution at the end point. Okay, that's how you can find out the reaction is completed. That means all the chloride ions in the solution have reacted with the AgCl. That is indicated by the indicator, because here AgNO3 reacts with the K2CrO4 and forms Ag2CrO4, which is actually a reddish brown precipitate. Okay, and here remember that the water sample what you are taking for the titration purpose, the sample water, right? The sample water must be neutral, or it should be a little alkaline, because silver chromate which is formed here, the silver chromate which is formed here, this is soluble in the dilute acids. Okay, this is soluble in dilute acids, so therefore we have to use the water samples which are neutral or slightly alkaline in nature. Now the tabular column is here you will be taking the water sample, maybe 10 ml I think, maybe here the 10 ml water sample, and initially purity reading 0, and a final volume it might be around 10 or 7 or 8 volume, and the difference substitute that value, because M2 value is given here 0.01 silver nitrate, M1, B1, N1, all these are given for water sample, M2, B2, N2 are given for silver nitrate. Substitute the equation and get the M1 value. Once M1 is known, multiply this with 35.5, divide by 10, that will give you the amount of chloride ions in the given water sample. And this is a very simple procedure. Of course, all the experiments we are just required and then do the calculations and submit. Understood?
Yes, ma'am.
Okay. Now just go through the Viva questions. What is precipitation titration, argentometry? Give some types of argentometric titrations. What's the role of indicator and how does the reticle appear at the end point? Oxidation number of K to CrO4. What is the role of dichromate ions in chloride estimation? Which range of pH is suitable for the chloride determination? So all this already we have discussed. You can read for yourself because already I have discussed about all of them. Yeah, any doubts in the experiment 4? Any doubts in the experiment 4? If there are yes or no, say something, girls.
No, ma'am.
If no doubts, I'll explain you how to write the record now. Shall I?
Yes, ma'am.
Yes, ma'am.
Okay. So the first page, do you have your records with you, girls? Do you have your records with you?
Yes, ma'am.
Okay. So first page, what do you see? Index page.
Index, ma'am.
Yeah. In the index page, what are the things you have? Columns, please read out once.
Serial number,
Yeah.
date of performing, title of
Okay. Very good.
experiment,
Okay.
date of submission, page
Okay.
number, remarks.
Okay. So what you can do is serial number, date of performing means you are going to write same date, 4 date same. Okay. The title of experiment, this one, estimation of hardness of water by complex symmetric method using DDTA. Likewise, you have titles for each and every experiment. So write down the title and date of submission, the same day because you are doing the experiment and you are submitting same date you can put. And the next page number, like you can start writing the page number from where you start writing the experiment number 1. Okay, so each page, each page, each numbering you will be giving 1, 2, 3, 4 like that. Okay, so experiment 1. So once the index page is done, then go to the next page. Now you have the empty page, right? You have ruled page, yes or no?
Yes, ma'am.
Yeah, just leave one page, and from the second page, start writing. So from second page, what will you write? Put the title as experiment number 1, heading as experiment number 1, then write the title, and like this, how it's written in the manual, the same manner, aim, apparatus, chemicals, principle, and draw the structure. Okay, structure you can draw on the left hand side, and then continue this entire principal part, continue this was entire thing continue, and then go to the procedure don't write step 3, write the procedure and just write what exactly is this estimation of total hardness of water, right? Estimation of total hardness of water. Put the title here. Likewise, how it is given in the uh, manual, you just follow same thing and write this entire theory part. Okay, write this entire theory part. And you have a tabular column. Can you see this? Can you see this tabular column?
Yes.
This tabular column has to be drawn on the left hand side. Followed by the calculations. Okay, till here. Till M3, you are going to write on the left hand side. Till amount, you are going to write on the left hand side. Fine. So starting from here till here, amount of total hardness in ppm has to be written on the left hand side. Okay. Then on the right hand side, what is that you are left over with? This theory part. Okay. Below you write the result. And then mention the amount of total hardness, how much you are getting. This you can write in ppm. Have you understood what I said?
Yes, ma'am.
Only the tabular columns, calculation part on the left hand side, and remaining everything should be written on the right hand side. And please do not copy the Viva questions. Don't write any Viva questions in your record book. This is only for your reference. Okay. Now once you have done with the first experiment theory part, take a fresh page and start writing the experiment number 2. Take a fresh page and write experiment number 2. Put the title AIM apparatus chemicals, how it is in the manual, please copy in the same fashion. And another important thing, like here whenever you have some equations, like this, you can write on the left hand side. Then chemicals required procedure, put the title here estimation of ferrous ion, draw the tabular column followed by calculations on the left hand side. Have you understood, girls?
Yes, ma'am.
So similarly the remaining experiments also.
Ma'am, what should we write in observation notes, ma'am?
No need of writing any observation. Directly come with your record book, lab manual. Another important thing is I want everybody to take a printout of the hard copy of lab manual, because only few pages are there, only 4 experiments. I want everybody to carry. So I won't allow you. That's it. So you have to come with your apron, white color apron you have to wear, girls. White color apron you have to wear, because you have to give your external exams also. Without white apron, we won't allow you. Okay, so get a white color apron, a record book, and a lab manual hard copy with you. Carry a lab manual hard copy. Am I clear? Please note down lab manual, record book, and apron. And another important thing is, I'm going to put the signature then and there when you come to the lab for each and every experiment. So if I see anybody without writing your record and getting the record empty for the lab, okay, you will be missing the marks for your record, girls. Because we are not making you to write anything in the observation, everything you are going to write in the record directly. So make sure that everybody has to complete their record before they are coming to the lab. Arshia, please pass this message.
Okay, ma'am.
Any doubts? See, only 35 participants are there. What about remaining 12? Absentees numbers you will note down, 8, 9, 10. They write down his absentees numbers 8, 9, 10, 14, 17, 19, 21, 24. Thirty, 31, 32. Roll number 29. Did you write your exam, ma?
No, ma'am.
What happened, ma?
Fever, ma'am. Dengue fever.
Oh. Did you contact HOD Aparna, ma, regarding this? Inform, ma?
Ma'am?
Did you inform HOD Aparna, ma'am, that you were unable to write the exam because of this particular reason?
No, ma'am.
Allah, mama, you have take permission, no?
I will inform CR, ma'am.
It's not like that, no. If you inform CR, what can she do? You have to inform to HOD Aparna, ma'am. Roll number 32, she's not there. 30, 31, 32, then 34, 36, 38, 32 also she didn't write her exam. 36, yeah, 36 absent, 38 absent, 41 absent, 43 absent, 44 absent, 52, 53, 55. Arshia,
Yes, ma'am.
did you note down the absentees?
Yes, ma'am.
Did you inform the Aparna ma'am regarding the absentees? Like this girl, she's saying that she has informed you.
No, ma'am. When we had a meeting, they told that if anybody is in a position that they can't take their mid exams, they will be conducted after SEM 2, ma'am. They said that they will personally look into that issue.
Yeah, regarding the lab internals also, like when we have the session, whenever it is scheduled 15th, so if you people are absent, I am not responsible. That information has to be given prior. Okay. If you have any problem, if you are unable to attend, that information has to be given prior. Otherwise, we can't help it. Because once the lab internal exam is done, we can't conduct again because we have external lab exams. Internal marks and external marks together, you'll be getting the final marks. So I want everybody to attend for the exam. If you have any issue, please inform it before the exams itself. So and so particular reason. So that we look into that issue. What to be done. Because your exam is on the last day, I think 15th. After that, immediately we have lab externals. So immediately, like whenever you have any issue, please intimate to the concerned faculty so that we'll look into that issue. Is that clear?
Yes, ma'am.